Last week, we wrote a kinematics unit test. And on that unit test, we used a lot of equations to describe the motion of objects. But what did we not pay any attention to? Yeah, what caused the motion? We looked at the motion itself without any regard whatsoever to what caused the motion. On Friday, we started talking about dynamics. That's our new unit. And in dynamics, of course, we're paying attention to what causes the motion. What is it, by the way, that causes motion? In other words, what's this unit really about? Forces, right. Dynamics is a study of motion with regard to what causes the motion, or in other words, it's the study of forces. How did you define a force in grade 6? It's a push or pull. It's the same way as you define it now, and it's the same way you're going to define it through the rest of your life if you ever take another physics course. It doesn't matter whether you're in an advanced third-year university class or a grade 6 science class, a force is a push or a pull. Now, it's not necessarily something that you're pushing. It could be the wind causing it to be pushed, or it could be a tow truck causing it to be pulled, or some kind of wind pressure difference that's causing it to be pulled as well. But it's always going to be a push or a pull. Now, what are the two things that a force can do? Don't say push an object or pull an object. That's what a force is. It's not what a force can do. What can a push or a pull result in? Jackson, what's one of them? Okay, it can cause an acceleration. What do we mean by acceleration? What does that include? Sorry? Okay, you could stop an object or slow down an object. Really those mean the same thing, right? An object's moving down the road or down the path or whatever, and it slows down. Well, if it slows down a little bit more, it stops. So it can cause an object to slow down and maybe even stop. What else can it cause an object to do? Yeah, Max? Well, let's look at acceleration here. Okay. No, I kind of misled you on that one, so that's okay. Yeah, it can cause a change in direction as well. It can cause an object to slow down or speed up, but it can also result in a change in direction. All of those things are within an acceleration or under the umbrella of acceleration. Max, what's the other thing that it can cause that a force can cause it to do? Right. And when we talk about deforming, a deformation, we're talking about it can squish it or it can stretch it. Basically, we're changing the shape of the object. Can it do both? Could it cause a change in direction and a change in shape? Or could it cause something to slow down and squish it? Absolutely it could. Okay, absolutely. There's two things that it can do. It can do one of them or it can do both of them. What's a net force? Remember the analogy we used with my net pay or with your net pay? What's the difference between gross pay and net pay, Laura? Yeah, it's the total force or the sum of all the forces. Sometimes we call the net force an unbalanced force. If the net force is 0, then the forces are balanced. Maybe you have a force of 10 this way, but a force of 10 the other way balances it, giving me a net force of 0. If we have a net force that's not 0, then we usually say we have an unbalanced force. Maybe you got a force of 10 one way and a force of 12 the other way, causing a net force of 2 newtons one way. Net force, unbalanced force. Another term, keeps on going here. Inertia. Every single one of us knows from Bill Nye the Science Guy in junior high school that inertia is a property of matter, but like, what does it mean? We don't want to just say it's a property of matter. We want to describe what inertia really is. Nick? Good. Inertia is kind of like describing how lazy things are. Okay? An object wants to keep doing what it's doing. It has a tendency to keep doing what it's doing. If an object is at rest, it wants to stay at rest. If an object is moving, it wants to continue moving or keep moving. So the objects are kind of lazy. They just don't want to change. You're at rest. Oh, I'm happy here. I don't want to go anywhere. I'm moving. Yeah, I'm happy doing this. I don't want to slow down or I don't want to speed up. Okay, inertia is that tendency to keep doing what it's doing. The tendency to maintain its current state of motion. Hey, what's this term equilibrium mean in either context here? You guys have heard that before in chemistry. We talked about it a little bit on Friday. Yep. Okay, so balance In the context of dynamics, what are we talking about balancing here? Not balancing some kind of chemical reaction, but yeah, we're talking about balancing forces here. So static equilibrium, forces are balanced. Translational equilibrium, forces are balanced. So what's the difference then between static and translational? Static means not moving. So if we're talking about an object in static equilibrium, we're talking about an object that's not moving, it's at rest, and has balanced forces. An object that's in static equilibrium has all the forces that are acting on it balancing off with each other. There's nothing unbalanced. What's that object going to do? I'm going to keep moving. Keep not moving? Can you say that? Keep not moving? It's going to stay at rest. Okay, the object that's at rest is going to stay at rest. It's in static equilibrium. It doesn't mean there's no forces acting on it. Right now, Nick's desk is in static equilibrium. There's forces acting on it. Hey, he's pushing down on that desk pretty hard, actually. Okay, probably with a force upwards of 700 newtons pushing downwards on that desk. But that desk isn't moving. It's in static equilibrium because there's an upward force of the floor pushing up on the desk of 700-ish newtons that balances that. There's forces acting, but they're balanced. It's at rest. It's not moving. There's balanced forces. It's in static equilibrium. And that desk, as long as those forces are balanced, as long as it's in static equilibrium, it's going to stay doing what it's doing. It's going to stay at rest. Translational equilibrium, here we're talking about objects that are moving, but the forces are still balanced. What happens to that object that's moving with balanced forces? Maybe Nick is sliding along the ice on his desk for some strange reason, and that desk still has lots of forces acting on it, but now there's still balanced forces acting on it. So nothing unbalanced here. What's going to happen to that desk is it's sliding along the ice. Sorry? No. That's a good. I'm glad you said that, though. Wouldn't it slow down was the question. No, it wouldn't slow down. As long as the forces balance, it will keep moving at a constant speed in a straight line forever. It's in translational equilibrium. If you're in static equilibrium, you're going to remain at rest forever. If you're in translational equilibrium, you're going to remain moving in a straight line at the same speed forever, until you're outside of translational equilibrium, until the forces are unbalanced, until one force is bigger than another, which could cause the desk to speed up or to slow down, depending upon which way it acts. Right? Static equilibrium, translational equilibrium, which lead us to Newton's first law, also known as the law of inertia. Newton's first law basically puts what we've just been talking about together for us. And it has two aspects, the law of inertia does. The first aspect talks about the object that's at rest. It says, an object at rest what happens to it? Finish that sentence for me. Stays at rest. Until, you guys didn't finish it for me, not until a force acts on it, until an unbalanced or until a net force. You say either one. Until an unbalanced force acts on it. Yep. What's a net force other than a value of 0 net force? Okay. So the question was, if you guys didn't hear this, could we just say net force as opposed to unbalanced force? Yes, I say the word unbalanced when I'm stating it because I think that leads to better understanding, but it means the same thing. If we say net force, and people are going to have the exact same question that you just asked, right? That is, couldn't it be balanced with a net force? No, if you have a net force, it's going to be unbalanced, right? If you have a net force of 0, we would say we don't have a net force, right? It's like saying, go to the grocery store and you leave and you say, how many apples do you have? Well, if you didn't buy any apples, if you have 0 apples, then you don't have any, right? If you have 0 net force, you don't have a net force, and the forces are balanced. What's the second aspect to it? An object in motion, right? An object in motion. And it's going to stay in motion, stays in motion. I'm going to put in brackets here, straight line. Same speed. So it's not going to speed up. It's not going to slow down. It's not going to change direction. It's going to stay in motion, same way it's going right now, forever, until, you could say until a net force acts on it, or you could say until an unbalanced force acts on it. I'm going to say until an unbalanced force acts on it. This first one is really just a restatement of this concept called static equilibrium that we were talking about. And the second one is really just a restatement of this concept called translational equilibrium that we were just talking about. An object in static equilibrium is going to remain at rest. An object in translational equilibrium is going to keep moving. It's going to keep doing what it's doing. Newton's first law, the law of inertia, you often hear it called the law of inertia. I sometimes call it the law of lazy things, because it really says that things are just going to keep doing what they're doing, not change, until they're forced to change by an unbalanced force. Sometimes we could call it the law of keep doing what you're doing, because things are going to keep doing what they're doing until something causes them to do something different. Yep. No, that's a good question. That's a good question. Let me tell you a quick little story about when I was 16 years old, got my driver's license. When I was 16, after I had my driver's license, only for a few months, I got a job driving a delivery van for a dry cleaner, which was for a 16-year-old who loved to drive, it was the greatest job in the world, driving a delivery van. I remember one Friday afternoon after school, I was driving this delivery van. It was winter time. There was some slushy snow on the roads. It was fine. I had driven in slushy snow before. And I remember driving on the highway and coming into this town to drop off some dry cleaning at this place, at this store. And I remember going to go exit the highway, go down this off-ramp like this, and the off-ramp goes around like this underneath the highway and goes into this town. You guys know what I'm talking about, right? Okay. So I'm driving down the road here, and I'm with one other guy at the time, one other guy that worked for the same company here, driving down at about 100 kilometers per hour. A little bit of snow on the road, but it's not too bad. Like, it's safe to drive that speed. And then I hit this off-ramp, and there's a little bit more slush on the off-ramp. So I slow down, of course, but then all of a sudden I hit a patch of ice on the off-ramp. What happens to me? I die. I'm still here. Yeah. So I'm going around this turn. I hit a patch of ice. What happens to me? Well, we have a tendency to keep doing what we're doing, right? We have a tendency to keep going around the turn, right? No, we don't. Because at any given moment, I'm not driving around a turn. At any given moment, I'm traveling in a straight line. But friction causes me to leave that straight line. An unbalanced force causes me to turn. If I hit a patch of ice right here, let's say, then that unbalanced force is no longer there. So that unbalanced force that was causing me to leave the straight line path and go in a circular path isn't there. That means that I'm going to go back to my current state of motion, which is that straight line path. So I'm going to keep going this way. No, I didn't go off because it was a guardrail. But my driver's license for, I think, about 4 months at that point, and I hit a guardrail right here. Yeah, it wasn't serious, but so an unbalanced force eventually acted on my delivery van, but it wasn't the force between the tires and the road that it should have been. It was the force between the guardrail and the front of the van that it shouldn't have been. One more. Another little story about me driving. Hey, listen, I'm not a bad driver. Okay, that one was my fault. Okay, that one was my fault because I was going too fast around the turn. But that's the only accident I've ever been in that was my fault. Okay, the first one, like I said, it was the deer's fault. The second one was my fault. This next one happened when I was an adult, and this one wasn't my fault either. And you'll agree with me on this one, I promise. You drive into Calgary, south end of Calgary there, the first set of traffic lights 15 years ago used to be in Shaughnessy, where they're building that new overpass now. Okay, that used to be the first set of traffic lights. Now they have that crazy traffic lights, and then 30 meters later another traffic lights, which makes no sense to me whatsoever. But the first set of lights used to be in Shaughnessy. And I remember one time, probably it would have been 15, 17, 18 years ago, somewhere in that range. I'm driving, I see the light turning red, I slow down, and I stop. The person ahead of me slowed down and stopped as well. The person behind me slowed down, and stopped as well. So I don't know how many people were behind me, but there was at least one person in front of me and at least one person behind me. Everybody stopped because you got a red light, because that's what you do when you have a red light, right? Well, all of a sudden, this lady that's behind me that was stopped because there's a red light and because there was a car ahead of her, which was me, stopped. She stopped. But then all of a sudden, although the light's still red, she decides to go. The light didn't turn green. She just put her foot on the gas pedal and went. Now, it doesn't make much sense that somebody could do that, although if you've ever, like, everybody's probably at some point been sitting at a stoplight and caught green out of the corner of their eye and took their foot off the brake, right? Because it's just like, you're not paying you should be paying attention, but you're not, you're just distracted by something, right? So it can happen, right? It can happen. Although I've never actually hit somebody like that. It could happen. I could see how it could. Anyways, she hits me. Now, thankfully, it wasn't a high-speed collision, right? Because she was not moving, and then she was moving at, I don't know, 5 kilometers per hour, less than 10 kilometers per hour for sure when she hit me. What happens? Well, my car jolts forward, right? Didn't cause any serious damage, but the car jolted forward because it was at rest in static equilibrium until an unbalanced force acted on it, right? Until another car hit it from behind. So the unbalanced force acts on my car and pushes my car forward. Now, I'm sitting in the seat, which is attached to my car. It pushes me forward as well. So not only does the car go forward because it experiences an unbalanced force, but so does my body go forward because it experiences an unbalanced force. There's one part of my body that does not experience an unbalanced force, at least not right away. What is it? My head. My head. I'm sitting at the stoplight. My body goes forward. What happens to my head? It gets thrown back, right? Like this? No, it doesn't. My head doesn't get thrown back like this at all. My head stays exactly where it is, and my body goes forward, which gives the effect of appearing as if your head is thrown back, right? Really, it's your head remaining where it is and your body going forward. That stretches the neck muscles, and that gives you whiplash. That's the whole injury of whiplash, is your head remaining at rest and your body going forward, and then eventually your neck applying the unbalanced force on your head. Why does your head remain at rest? Because everything remains at rest until an unbalanced force acts on it, right? Anybody ever had whiplash getting hit from behind? Yes? Bumper cars, yeah. Yeah, absolutely. In fact, bumper cars actually, bumper cars can be nasty actually sometimes. Sometimes bumper cars are actually I actually sometimes don't like bumper cars because they're so rough. Like I'd rather go on a roller coaster sometimes that's got a 50-meter drop than a bumper car and get hit from behind by somebody, especially when you're on there with a bunch of students and everybody's going after you. Listen, guys, I got a few questions for you to work on here. I think you have a bit of an understanding right now as to Newton's first law and this whole idea of equilibrium and translational static and so on. I want you to work on 5 questions here on page 142, questions 1 to 4 and question 6. We'll give you a few minutes to work on those in class. Take a look at a couple of them, and then we'll move on to something else. All right. We've talked about things in equilibrium when we're not accelerating, right? We've talked about balanced forces, net force of 0, translational equilibrium, static equilibrium. An object wants to keep doing what it's doing. But then sometimes it doesn't keep doing what it's doing. Sometimes there's something that causes it to accelerate. And it's not in translational equilibrium or static equilibrium. What is it that causes the acceleration again? What is it? Force. It's a net force. Not a force, but a net force. Okay, right now, there's no net force acting on the desk. The desk is at rest. It's going to stay at rest. There's a force acting on the desk, though, so it's not a force that causes motion. It's a net force or an unbalanced force that causes motion. But what does the acceleration depend upon? The force gets it accelerating, but what does the value of the acceleration depend on? How do you make the acceleration bigger? How do you make the acceleration smaller? There's 2 things. The acceleration is directly related to, ever seen that symbol before? Okay, it could be a fish. Yeah. Yeah. It's directly proportional to, which means that as one thing gets bigger, the other thing gets bigger proportionally. If I double whatever appears on this side, then this doubles. If I cut this by a factor of 3, then this gets cut by a factor of 3. If I increase this by a factor of 16, then the acceleration goes up by a factor of 16. It's a linear relationship. What is acceleration linearly related to? Not force, but you're close. Nope, you're closer. You're getting colder now. Nope, you're getting colder. Colder, colder, colder. Net force. Net force. You knew it had to be the net force because somebody commented before that this was like a fish, right? So you knew it had to be the net force, not just a force, but the net force because you can't catch a fish without a net. It's directly proportional to the net force. And that means that it's also in the same direction. So if the net force doubles, the acceleration will double. And if the net force is to the right, then the acceleration is to the right. If the net force gets cut in half, then the acceleration gets cut in half. If the net force is to the left, then the acceleration will be to the left. Now the net force, so the acceleration is directly proportional to the net force, but it's also related to one more thing. What do you think it might be? Well, no, but we alluded to it earlier today. Inertia? You're close. You're really warm, actually, on that one. What is it that is responsible for inertia? Mass. The acceleration is not directly proportional to the mass. Rather, it's proportional to the inverse of the mass. In other words, as mass goes up, what happens to the value of acceleration? It goes down. You ever try pushing a little smart car? You probably can accelerate that. You could probably cause that smart car to move. You can probably accelerate that smart car. You ever try pushing a semi-truck? Even if you could get it moving, it would accelerate at a much, much lower rate than the smart car would, right? Because it's got a much lower mass. Increase force, increase acceleration. Increase mass, decrease acceleration. We're going to put these 2 together and say that acceleration is equal to the net force. Even though we took away our little fish, we still have the net, divided by the mass. This is our 6th group B equation. I want you to take a look at your data sheet for a second. In Unit 1, our kinematics unit, we circled our first equation, v equals delta v over delta t, and called it group A, because it was valid when we had a constant or average velocity. The other 5, vf squared is equal to vi squared, and so on, we called those our group B equations because they were valid when an object was accelerating. We now have another equation under dynamics, which is this one, although in a rearranged form. The net force is equal to the mass times the acceleration, which we're also going to label a group B equation. Now we got 6 of them. It doesn't really change anything. We just have more tools in the toolbox now. If you're given force, hey, now we can deal with that. Doesn't mean the other equations aren't valid. We'll still use them. Okay, you're still going to use A is equal to delta V over delta T and so on, maybe to find acceleration so that you can plug into here. It's like we did in the last unit, right? Sometimes we had to use 2 equations. No different, except that one of them now will usually be F is equal to M times A. Remember that when you see this equation, that F doesn't stand for force. That F stands for net force. You don't usually see it written with the subscript net there, but that's what it means. Net force, the total force, the unbalanced force. Sometimes there is only one force, and if there's only one force acting, it is the net force. But if there's 3 or 4 forces acting, then we have to have the combined force, the net force, the total force, the unbalanced force. All right, let's do a question here. Or sorry, let's restate what we just said in words, which is really Newton's second law. We said that the acceleration was directly proportional to the net force. It's directly proportional to or directly related to the net force. And what I mean by that is that as the net force doubles, then the acceleration doubles. As the net force is to the left, the acceleration is to the left. So proportional numerically, but also proportionally directionally to the net force. And it's inversely related. Is that spelled right? Inversely? Yeah, close enough. It's inversely related to the mass. Mass is a scalar, so there's no directional component to this. It's just a matter of if mass increases, then the acceleration of the object decreases. And what it boils down to is an equation. A is equal to F over M, which usually we rearrange. Take this form, F is equal to M times A. This is the way that it appears on our data sheet. And one final reminder, that force is the net force. If you got a force of 10 newtons acting on an object and a force of 30 newtons acting in the other direction, our force isn't 10 or 30, our net force is 20 that we will plug into that equation. All right, let's now do that question that I was just talking about a minute ago. Page 149, it says a lacrosse player exerts an average net horizontal force of 2.8 newtons forward on a 0.14 kilogram lacrosse ball. So there may be 2 or 3 forces acting on this lacrosse ball, but they're telling us in this question that the net force acting on this lacrosse ball is 2.8 newtons. Okay, that's good. We don't have to figure out the net force, the combined force, because we already have it. We're going to find the average horizontal acceleration of the ball while in contact with the net. This is a group A problem or a group B problem? It's B because it's accelerating, right? We know that all of those acceleration equations that we learned in our last unit are valid now, but we're probably going to use F equals ma, right? Let's write down some givens. We'll say the net force is 2.8 newtons. The mass of the ball is 0.14 kilograms. Looking for the acceleration. Sure enough, F equals ma, or A is equal to F over M. You get 2.8 newtons over the mass. I think that gives me 20. Is it 20? What are the units? Meters per second squared. Or Max? Yeah, that's a good question, actually. Yeah, mass needs to always be measured in kilograms. 20 meters per second squared or 20, no, good guess though. Newtons per kilogram. Newtons over kilograms. Means exactly the same thing. So you don't need to worry about converting newtons per kilogram to meters per second squared. 1 Newton per kilogram is 1 meter per second squared. Use whichever one you want. Okay, I usually use meters per second squared because of habit, but it's not better than newtons per kilogram. It's just habit. They're both correct. Yep. Could you ask that again? Well, you couldn't replace newtons with kilometers because newtons measures force and kilometers measures distance or displacement, right? Grams. Yeah, okay. If you had, instead of kilograms, you had grams, you could technically say newtons per gram for acceleration. I don't want you to do that though. Okay, if you have grams, I want you to convert to kilograms. And then once you convert to kilograms, by dividing by 1,000, you're going to have newtons per kilogram or meters per second squared. Okay. You can talk about newtons per gram or newtons per kilogram. It could actually work. But when you're dealing with meters per second squared, it becomes ugly because of the square on the bottom if you start using other units. All right? And of course, in the end, whenever we use acceleration for anything else, it's got to be these units, right? So we might as well just get those units right off the top. Okay, try these two questions, please, on page 149. All right, so you guys seem to think you're so hot doing those questions. Let's try this one. This one's not in your textbook, but it's okay. So it says a 1,000-kilogram car moving at 72 kilometers per hour slows to a stop in 10 seconds. How much force was required to stop the car? What should I really put in front of the word force? How much net force? Because there's multiple forces acting on this car, right? How much net force is required to stop this car? All right, is this a group A problem or group B problem? It's group B. Clearly this car is decelerating, it's slowing down, it's stopping, right? So it's a group B problem that involves acceleration. Well, we know we have now 6 equations that are at our disposal for group B, those 5 that we learned in our last unit, and now F is equal to M times A as well. Okay, now that we know what's going on in the question, let's write down some givens, and then we'll try to figure out which equation or equations are going to help us to solve this. We have a mass of 1,000 kilograms. We have something that's 72 kilometers per hour. Can you tell me what that is? V, velocity what? Velocity what though? It's not just velocity. Velocity initial, it's going to be VI, yeah. And of course, we're going to want to convert that to meters per second. We're going to do that by multiplying by 1,000. 72,000 divided by 3,600 gives me 20 meters per second. Question, Isaiah? Absolutely, a force can be negative. Yeah, in fact, this force is causing the car to slow down, so we should end up getting a negative force there. It's a good observation, okay? We don't have to necessarily recognize to solve for force, but if we solve for force and we've already predicted that it should be negative, it's a nice little check for us, right, to make sure that we've done it right. What else we got here? 10 seconds, the time interval is 10 seconds. Anything else we have if we read between the lines here? What is it, Max? Yeah, VF is 0. It stops, right? So VF is 0. And we're looking for the net force, F. So what do you want to do to find the net force? All right. Yeah, okay. In the end, it doesn't matter which way you go first. Okay, I tend to, when I see something like this, say, oh, look, I'm looking for the force, so I'm going to use this equation. F is equal to M times A. But I don't have the acceleration, so I'm going to have to find that some other way. Now, what Simon just said is, Simon said, let's get the acceleration and then do the force. So it's kind of just a slightly different way of thinking, right? Get one then the other, or try the other and then say, oh, I got to get the first one, get the acceleration. Doesn't matter what order you try it in. Okay, we got to find acceleration here. How are you going to do that? Yeah, let's just go delta V over delta T. Although all those other equations are still valid. Delta V is VF minus VI, 0 minus 20. As you're starting to see what's going to happen here is in response to your question that you asked a minute ago. 0 minus 20 over a time interval of 10 seconds gives me an acceleration of negative 2.0 meters per second squared. Why negative 2? Because this car is slowing down, right? Now we're going to plug that into this equation, and we end up with a force of negative 2,000 newtons, which it should be a negative force, right? Because it's causing the car to slow down. Now, how many digits should we round that to? 1,000 is 4, this is 2, this is 2. Final answer should be 2 digits. Negative 2 times 10 to the 3 newtons. You could say positive 2 times 10 to the 3 backwards, right, in the negative direction. Yep. No. Sorry, that shouldn't be 10 to the negative 3. That should be 10 to the positive 3. You can do negative exponents, but a negative exponent would mean that would have been 0.002 newtons, not 2,000 newtons. I moved the decimal place in the wrong direction, basically. Yeah, by a factor of 1,000,000. Listen, hey, I nailed that question. I was only off by a factor of 1,000,000. We're good? Easy stuff, right?